Excellent. So thanks everyone for coming. My name's Ari. I'm from the Darling Downs Environment Council, not cancer. And yeah, we're very grateful tonight to have two experts in fields of renewable energy, safety and recycling, Dr. Deepak Mishra and Dr. Rong Deng. Is that right? You're both doctors? Excellent. Yeah, cool. To present to us about solar panel recycling, but also battery safety as well. Um, and yeah, before I go any further, just want to acknowledge the country where we're on here with the Darling Downs, that we're on the Guyabul and Jarawar country of the Western Waka Waka, and just acknowledging our elders, the local elders, past and present, and their custodianship of country and community, and their sovereignty has never been ceded. Yeah, and just acknowledging all of our spiritual and cultural connection to the land that we're on and desire to steward and look after it. And yeah, you're welcome to introduce yourself on the chat, um, and yeah, say hello and who you are and where you're from on there while we get started. And welcome to introduce yourself later on when we have questions and discussion after the presentations. Just a short bit of context. Darling Downs Environment Council has been kind of doing renewables done right advocacy for the last um, yeah, just over a year now. And that's focused on trying to advocate for better renewable energy regulation and planning to address issues and iron out the what to improve the way it's being rolled out in regional communities. So that's included consultation with different community stakeholders, organising a big forum in Toowoomba that we had in March last year, going for grants and funding. We were then lucky to get Megan Brady, who's on the call with us today, working um, on the local engagement partnership program that QCC, Queensland Conservation Council, is running. And we got a grant to get her working with a local focus a day a week around education and engagement. And she's been keeping a close eye on different projects and finding out community concerns and identifying what environmental outcomes and solutions are required to ensure projects are located and developed in the best way possible for nature and for communities. And that's about to culminate in the release of a booklet that is very much designed to address a lot of the misinformation issues around renewables that we're hoping to distribute to many, many people across southwestern Queensland by direct mail if we can fundraise or find the money for it to get it in their letterbox. And yeah, so that's currently what we're working on. And yeah, it'll be very interesting to learn about what we're going to learn about today from Deepak and Rong. I think Megan found that just recently there's been some breakthroughs in wind turbine blade recycling technology, which is exciting because up until recently, apparently that's been one of the bits that aren't very recyclable about renewables. Um, so that's good to know. And yeah, we're really keen to find out where solar recycling looks like it can go in Australia and what options there are, and also battery safety as well, because that's also a big learning curve for society as we manage increased battery use. So yeah, before yabbing on for too long, I'd like to welcome again Deepak and Rong, Dr. Deepak and Dr. Rong. Who would like to go first with your presentations?
Yeah, either way works for me.
So, you pick.
Well, let's go with Dr. Rong, and we'll just start off with. So I'll turn on so that you can share screen. Yeah, and Wait a second, I need to make it so participants can share screen. How do I do that? There we go. You should be able to share screen now.
Yep. Let me. Oh, where is it? Too many things on my screen. Give me. Don't have that many things. Wow. Well, I'll just share my whole screen.
Yeah, that's all right.
Yeah, I'll share my whole screen. And oops. Can you see my slides?
Yeah, yep,
Okay. Can you see my notes now?
yep.
Okay, I'll turn back. All good.
There we go. We can just see your slides now.
Thank
Perfect.
you. So thanks for the invitation. I'm very happy to be here with all of you today to talk a little bit on solar panel recycling. It's definitely a growing problem, and we've seen more and more and more about it on media. So this presentation is about solar waste to circular value. What if we change our perspective to don't see them as waste anymore, but rather we treat them as resources to support a circular, sustainable energy future? Before I start, I'd like to acknowledge Badigo people as the traditional custodians of UNSW Kensington campus, where I sit on today and in the past 12 years. We pay our respect to their elders, past, present, and emerging. My name is Dr. Rong Deng. I wear many different hats. I'm a research fellow at School of Photovoltaic and Renewable Energy Engineering, UNSW. So for those of you who don't know, UNSW invented the world most commercial solar panel technology called PERC. So UNSW's research group at our school invented this technology in 1980s and now used in more than 90% of commercial solar panels. The same research group continued, and actually last year we celebrated the 50th year anniversary of that solar cell research group. I'm also a lecturer at University of New South Wales, and the course I teach is life cycle assessment. I also wear straight other hats. One, Australia lead on International Energy Agency Photovoltaic Power System Task 12, which I'll talk a little bit more on that. I'm also director of Australian PV Institute. If you want to find PV installation data in Australia, you want to use a sunspot tool to map out your solar potential on your rooftop, that's what the tools we can provide on Australian PV Institute. And very recently, 10 months ago, I started my own company called Hello Against Solar. So Hello Against Solar is an Australian deep tech company to develop and commercialize a laser-based delamination technology for high-value solar panel recycling. For me, I've been researching on solar panel end of life and recycling since my PhD, which was 8 years ago. And that has been my only research interest to date. So that's pretty much all I deal with, all I research in the last 8 years. And I'm very happy to answer questions at the end, which are not covered in this presentation. So a little bit on IEA PVPS. International Energy Agency was founded in 1974 to support and encourage more international level collaboration. The Technology Collaboration Program was created to get a group of experts from different countries to talk about some common themes in energy transition. So where I sit as Australia lead is Task 12 PV sustainability. In this task, we have experts from 14 countries, and we talk those common issues of solar on circular economy, which covers recycling, reuse, repair, environmental life cycle assessment, not just carbon emission, but land usage, acidification, how do we contaminate the land, and how can we improve the environmental impacts of solar. Also, other applications like floating PV and agri PV, as well as other social and socio-economic issues. So in TOS 12, we have 31 experts from 14 countries and 5 companies. Myself, Professor Ian Song Shen, and Dr. Mo Yong Kim, 3 of us represent Australia on this panel. So what we do is we meet twice a year. We update each other on what's happening in the country and also learn from other countries what's happening. Because, for example, solar end of life, this problem will definitely happen for all of the countries, but the timing is different. For Europe and Japan, they started solar in 1990s, and they are already facing this end-of-life problem. Australia, we start to feel it, and countries like China or India, they started solar industry much later, and they will experience that problem much later. Through this international collaboration program and expert representation, we can learn the lesson from other country to fast and better solve the problem in our own country. Task 12, we publish a report. We publish all the best knowledge reports. It's a really good library and source of information if you want to know more about, say, solar recycling, solar panel reuse, environmental impacts of solar in and outside of Australia. Everything is publicly available online, and there are a collective effort of 31 experts from 14 countries. So that's all about IEA PVPS. The reason I want to introduce IEA PVPS is we publish everything. So if you really find today's presentation interesting and you want to see a little bit more, here is a website, here is a link, here is where you find the information in and outside of Australia. But for today, let's focus on Australia. If I talk about international, I need another 4 hours. Today, let's focus on Australia. So from solar waste to circular value, where we are and what's ahead, I'm going to cover the 3 topics, and many of them will refer to a scoping study, Solar Panel End of Life Management in Australia report we published last March. Again, this report is available online, and if you're interested in some data, some statistics, some of the modeling tools, you can find this report online. Why solar waste matters, and why now? We estimate 2 million solar panels will retire in 2025. That's 2 more months to go. And this is growing. We've seen how fast solar installation grow in the past. The same curve will happen when those panels retire. In the next 5 years, this volume will grow to about 1.2 gigawatt per year. To put it into perspective, we already know that Australia is installing solar at the fastest rate ever. Last year, we've installed 4 gigawatt. And in 5 years, we will retire 1 gigawatt. That's a quarter of what we're installing today, which means a lot. And if we look at where are they coming from, most of them, as seen in this figure, most of them are coming from rooftop systems. The smaller system sitting on everyone's rooftop. There are 2 reasons for that. One is Australian PV market started with residential in about 2010, and those panels or those systems are retiring now. Utility scale system, we've only started around 2017, 2018. They're only 7-8 years old. The technical lifetime of panel is 25 years, which the 7 and 8-year-old panels are perfectly fine. But on top of that, from our research, we find the practical lifetime of panels are very different in small and large scale system. For small scale system, it's like a consumer product. The owner, him or herself, can make the choice of getting rid of it and replacing with a new one. So just think about last time when you replaced your phone. Was that really because of your phone was completely dead, or you just want to change to a new phone? So the same reason applies when residential owners want to upgrade their system. It's not because the panels or the system are technically dead. It's because they just want to upgrade it. They want to upgrade it so that their system can generate more power. They want to upgrade it to get better, more reliable, higher quality products. Or they are demolishing the house, so the panels have to be taken down. And in contrast, for large-scale PV system, they are usually designed to last for 20 or 30 years, 25 to 30 years with a certain financial return. To replace that system, you need to convince your bank, convince your insurer, convince your finance person, convince your CFO, I need to replace it. And this is not easy. So most panels, unless there is a weather disaster or other occasional events, panels in big scale system will last for much longer. Taking that into consideration, we can model the volume of panels coming off in the next 25 years. So why we care about that? Because solar panel contains certain valuable materials, and I have a slide later to show what are the valuable materials. If we address all the technical challenges in recycling solar panel today, and we actually recover all the valuable and critical materials from these panels, we can potentially unlock a material sales revenue of over $1 billion by 2033. And well, the biggest environmental problem for solar panel is not energy, is not carbon emission, because running solar, we need sunlight, we don't really generate much carbon. But the biggest environmental problem for solar is it's resource intensive. To make solar panels, we need lots of aluminum, lots of silicon, lots of extremely high energy to make those panels. And they also need area, a huge land to deploy, to generate the electricity. So for solar, the biggest problem is it's resource intensive. And based on current trajectory of how many more solar we need in the future, we are very, very likely to deplete the world reservoir of silver and a few other materials just to meet the demand in the future. So where are we going to find all those silver if we are going to run out of silver on Earth? Well, one way is to find that silver from the waste. Because even though solar panel technology change and the efficiency keeps improving, the material and the configuration of a solar panel does not change that much from today than 40 years ago. So what we can do essentially is to get the same material recycled to make new solar panels. Let's take the most ideal case. Every solar panel is recycled and all the materials are returned to a status that they can be used, not returned, recycled in a status that they can be made into a new panel. In 5 years' time, we can meet 30% of our installation demand purely based on this waste reservoir. In 25 years, we can meet 100% of our future PV installation demand purely based on this waste reservoir. That means we don't need to dig out more silver and other critical materials from Earth to make more solar panels for the energy transition. We can dig out from our waste reservoir, and that's self-sustaining. This self-sustaining ecosystem will last for not just the next 25 years, but forever. But to be able to do that, we need to start today or as early as possible. And that is not a lie. Last October, Trina Solar launched the world first 100% world first solar panel made from 100% recycled material. That means the glass, the aluminum, the silver, the copper, the silicon, all the materials use 100% recycled materials. Pretty much this technically validate that materials can be 100% recycled to make new panels at almost the same output and efficiency as standard commercial panels. And while we may think that this is a future problem, because solar panels last for 25 years, and everything I described so far, in 25 years, we don't need to dig up more silver. In 25 years, we have this billion-dollar industry. But this is actually affecting people, especially the regions right now. I don't have a date there. So earlier this year, May 2025, a town-sized solar farm, 100 megawatt, was cancelled in Yass, New South Wales. Yass is a town close to Canberra. International energy provider ENGIE was planning to build a 100 megawatt solar in Yass. But locals were told that panels cannot be recycled, and all of this town-sized solar farm, the panels, everything will be left on their land forever. Of course, locals push back. They don't want their town to be full of panels in the next 500 years. They pushed back. Addressing this social concern and addressing end-of-life solar panel recycling and transportation cost at the project total cost by about 10%. That makes Ya's project less economically attractive than overseas alternative. And as a result, ENGIE cancelled this town-sized solar farm. That's 200 million Australian dollar investment gone. This whole new industry, the solar farm, the local opportunities are gone, disappear in Yas. So even though it sounds like a future problem, but if we don't solve it now, we will watch more solar projects in regional Australia disappear, like Yas. So that's why solar waste matters and why now, because it is happening. And only if we start solving it now, we will have a true circular future and a circular economy in the future. Then the second part is what's already working and what's not working. What is the regulatory landscape in Australia? There are a few iterations. So at the beginning, we want the industry to come up with a scheme that the industry, different participants agree with each other who's responsible for end of life, who's paying, who's recycling, what is the cost, etc., etc. But industry participants never agree with each other. So in 23, federal government, federal DQ, that's what's 2022. Federal DQ decided to turn it from an industry voluntary scheme to a regulatory scheme, and federal DQ is leading that. They are consulting with industry to come up with a happy scheme design. The scheme is called Product Stewardship Scheme. But again, they made limited progress, and the main reason is because in the industry, everyone think very differently. So the latest update was August 25. New South Wales DQ is now leading this national effort by doing the first regulatory impact statement. And I've been helping with this whole process since 21. I've helped this voluntary scheme. I've helped federal DQ on their scheme, and now helping New South Wales APA on this new regulatory impact statement. And a lot has happened, but it's really hard to find a scheme that everyone is happy about. So that's the latest media release from Minister Penny Sharp. And she cited the volume of end-of-life panels in New South Wales and in the country. And this number is from the report I showed earlier, the scoping study, Solar Panel End-of-Life Management in Australia, that we published earlier last year. So what's in a panel and what's recyclable? Conclusion first, solar panel is 100% recyclable, so don't worry. Whether the technology, how good is the technology, that's something we can discuss, but a solar panel is recyclable. It's not scary. It's not something that would be left on the land for the next 500 years. It is perfectly recyclable. And the left-hand side shows the configuration of a panel. About half, or a little bit more than 50% of the value is trapped in the middle, very thin 5 to 10% of the weight. And the aluminum frame and glass and the junction box is about another 50% value. So because of this structure, The technical challenge to fully recycle a solar panel is how to get to the middle value. Because solar panels are designed to last 25 years outdoor, it is very rare that any products we use every day can last 25 years outdoor, which means panels are designed to last long in harsh condition. That means it's also hard to break that harsh structure to get to the valuable materials. Recycling is not a single step. Recycling has its own supply chain or ecosystem. So firstly, the owner needs to decide, I want to decommission my system. It can be, I just want to decommission my system, or panels are dead, or there's a hailstorm. I have to decommission my panels or my system. Then someone need to collect it. This collection person may drop it off at a temporary drop-off point, or best case, take it directly to a recycling and reuse factory. And after recycling is not magic. Recycling is not make materials disappear. Recycling is a process to turn something people don't want into commodities other people can buy. And those end market buyer will buy recycled materials and make them into new products to complete the full cycle. In recycling, we have three major steps. One called first is disassembly, delamination, and material recovery. So for the industry to implement recycling, there are two main approaches. Industry can just do the first two, which is relatively easy and already happening, or they can choose to do all the three steps, including the last hard step. The last hard step costs a lot more than the previous two and needs much higher technical, for example, chemistry, pyrolysis, expertise to recover all the critical materials at a high quality and high yield. So this is a simple look of what it looks like: disassembly, delamination, and material recovery. This is what actually happens. Disassembly, let me turn on my laser pointer. That's disassembly. This is delamination, and everything else is material recovery. They can involve high temperature or hazardous chemical, or a combination of both. And after this chemistry, you also have this problem of chemical disposal, metallic contamination in your water, and how do you deal with all that with your landlord and your environmental regulatory system there. Okay. So in Australia, by October last year, there are 7 companies doing solar panel recycling, and you can see all of their locations here. In addition to all the industry efforts, Australia also invests heavily in R&D in new innovative solar panel recycling technologies. There are research grants, there are research commercialization grants, or infrastructure funding to support established domestic solar panel recycling capability. So for example, New South Wales EPA Circular Solar Grant provided $10 million, and as a result, we have PV Industry, Circle, and Blue Tribe have core capability to recycle solar panels in New South Wales. If you want to know more about the technology, because I pretty much skipped all the technology details. If you're a technology person, you want to read more, you want to know how that chemistry works, how that pyrolysis works, here are the 2 best resources I would recommend. And this I can probably skip if you're not a researcher, but pretty much this is showing how many papers we're publishing on solar panel recycling every year, and that's an increasing trend, no surprise. And the left one shows how many pilot scale solar panel recycling trials are happening. So those are one step further than just doing it in the lab. Last part, 4 big truths I wish everyone knew. First, recycling costs money. I mean, solar panel recycling costs money. Well, because in this presentation, I keep saying it's a resource. We recover silver. There are $30 worth of value, blah, 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 blah. But solar panel recycling is a new industry. When the product for any new industry is expensive. 10 years ago, when Tesla sold their first Model 3 car, it was 5 times more expensive than Tesla Model 3 today. Same thing here. Solar panel recycling, it's so new. And at the beginning, the cost is high, it's expensive. In Australia today, the typical cost to recycle a solar panel is $10 to $12, and the user have to pay a transportation fee on top of that. And recycling also needs some sort of volume to break even. And this volume is, at today's level, a little bit hard to achieve unless it's a really innovative technology. So if you own solar and you want to get rid of it, and your installer or whoever's taking away your panel charge you, don't be surprised. It is very common because it's a new thing. If you don't want your panels to go to landfill, you want all the materials to be recovered, to be properly treated. There is a fee, and the fee is about $10 to $12 per panel. But the cost will drop very fast as we scale. It is expensive just as of today. Same example, Tesla Model 3. Tesla Model 3 was 5 times more expensive 10 years ago. But as they make more cars, sell more cars, they improve their engineering design, they learn as they go, and the costs come down really fast. The beauty of recycling is we need some money to run the operation, but we also recover revenue. We also recover revenue from those materials. The cost will go down, the revenue will go up as we improve our recovery yield. So in my view, in the next 5 years, we will reach that cost parity. And another thing, the most valuable content, material in a panel is silver, but the content of silver is shrinking. Newer solar panels use much less silver. It doesn't mean we should stop recycling panels. It just means for a recycler, if you want to enter this industry, you have to be aware of that. You can't assume all solar panels will have the same amount of silver as 15 years ago. We've done this experiment under New South Wales EPA's grant with Circle. We picked 24 panels of very different year, different manufacturer, different look, and we looked into the materials in each panel. The paper is under review, but for the audience here, the key information is there is huge variation in valuable material concentration across different panels. And finally, end market, it's very hard because recycling is not about making materials disappear. It's about making materials into commodities that other people can buy. But in Australia, we don't have a huge end market that is happy to take commodities from recycled panels, even they are at high purity. So for example, glass. The most glass recycling in Australia is bottle glass recycling. And we already have more bottles to be recycled than our existing glass recycling capability. And those glass bottle recyclers can't be bothered to take more solar glass because they already have more than enough. So unless we solve the end market challenge, we cannot close the full loop. So some solutions are to come up with creative products with those commodities to monetize on the whole recycling industry. And another reason why this is so hard is because in Australia, at least today, we don't have solar panel manufacturing. We don't have many solar panel manufacturing and its supply chain capability. So even though theoretically, and this is happening overseas, as the recycled solar panel glass can be added in the solar glass manufacturing line to replace some of the virgin material. But we don't have that line in Australia, so we can't integrate it that way. I think it's almost at the almost the last slide. So I talk a lot about what's happening in Australia, opportunities, challenges, why and what could happen. If you want to know more about other countries, again, IEV PVPS is the best resource. We've already published the best knowledge, best practice in Germany, and there are a few France, China, Spain are all publishing their best practice in the next 2 years. So the takeaway message is, firstly, solar panels are recyclable. They are not scary. They are a perfect resource reservoir to support our clean energy transition. And clean energy doesn't end at generation. It ends at circularity, because there is a chance, and it's 100% doable. At the end, we recycle all the materials and make them into new panels and shine again. So at UNSW, we recently started a new research project called Shaping the Future of Utility Scale Solar Decommissioning. So we are calling for asset owners and developers who have current solar asset or developing new utility scale solar projects to think about decommissioning ahead of time. Just to give you a example, I went to All Energy in Melbourne last week. And before I went to airport, I dropped my phone in water. As soon as I landed, my phone was completely dead, and I was in a new city. I did not expect that my phone would die on a trip, so I did not bring any credit card. I did not bring any ID. I don't know what is my hotel. My phone entered accidental end of life with very randomly. So what I'm saying is this could also happen to a solar asset. For example, in WA, there was a 10 megawatt offshore solar co-located with a mining site. The mine was shut down, and without previous signal, that solar farm was decommissioned. The asset owner was so surprised, just like me. They have no idea what to do. So continue back to my phone story. My phone was completely dead. I did not have a credit card. I did not have an ID. I don't know where is my hotel. I need to buy a new phone so I won't get lost in Melbourne. When I went to Apple Store, I realized without my phone, I couldn't even pay to buy a new phone. So again, the same thing could happen to a solar asset. The asset owner could face accidental end of life. And on top of that, another layer of challenge is they don't have the money ready to address this accident. So what we are developing here is a comprehensive decommission framework to help asset owners to think ahead. What if, to think ahead, how to plan end of life. So for me, if I knew that my phone would die, I would at least bring a credit card or bring a backup phone so that I won't be so surprised when I was completely lost in Melbourne. So even you are asset owner or you know any asset owner who hasn't decommissioned any or it's so far away from decommissioning, but we will welcome any utility scale solar developers, operators, asset owners to join this research so we can plan this framework ahead to help them to budget ahead, to know what's ahead of time. So when it actually happens, they have a budget, they have a plan, they know what to do, and they won't be completely lost when it happens. So if you know anyone who might be interested in this research, here is my email and my PhD student who's doing this work. So feel free to contact us or put us in contact with the best person you think might be interested in this. And Hello Against Solar is a spin-off company from UNSW. We develop and commercialize our innovative laser-enabled decommissioning technology for high-value solar panel recycling. We are supported by Trailblazer Recycling Energy and UNSW founders. We currently offer three services. First is decommission cost estimates. For current asset owners who want to refinance or sell their current asset, they have to recognize decommission as a liability. If you know anyone who has this problem and they don't know how to estimate this liability, talk to us, we can help. We are also launching our certified recycling service late 26 in New South Wales. And the third pillar is training, education, R&D capability, like what we're doing today. If you have a group of people who needs to upskill themselves on solar end of life, solar decommissioning, or have any small R&D projects they want to do together with Hello Again or with UNSW, we are all here and happy to help. I believe that's my last slide. Okay, thank you.
Wow, Rong, thank you so much. That was amazing. So many questions.
I can't find
Um,
you.
Yeah, really good. The question now is, do we write down our questions and go through Deepak's presentation, or go through them all at the end, or do some questions now and then go to Deepak? Does anyone have strong opinions? Do some questions now. Okay, that's probably a good idea. Oh my God, I've got so many. We might need to start like a fact spreadsheet. Does anyone want to raise their hand to ask the first one? Trevor, yeah.
Yeah, I'm just curious as to how much of the recycling will come into the remote areas, because I've got my house is under full solar with the battery backup because of them incentives, and it took us forever to get that system. I presume the same will happen with the solar recycling as well. That's
Even
all.
worse.
Okay.
So, from my understanding, there's no regional recycling service for rooftop system. Solar farm is different. If they can
Yeah.
give recycler 10,000 panels in one go, then someone is happy to come on site and collect it.
Yeah.
But if you only have 10, 20, no, unfortunately, no today.
No worries.
Can the intact glass sheets be collected and resold for glazing?
I don't know. I don't know what's glass glazing. Sorry.
So I see it kind of relates to my question. You mentioned in the presentation that the glass could be used for like concrete as an additive. Does that mean it can't be returned into glass again?
It can, because we can recover the perfect glass sheet, but we don't know what can we use that for. Because to make new glass, I think the input, they only take cutlet as input. Glass manufacturer don't really take full piece of glass as input. Oh, okay. So the difficulty is solar panel glass is tempered glass, which means they can't be cut. If you cut it, the whole thing will shatter. So they can't be resized.
But can you like shatter it and crush it and then give it to a glass manufacturer that makes bottles or something like that?
Yeah, technically yes, but like I said, those glass bottle recycler already have too much to deal with, so they don't want to risk taking new feedstock, which can then affect the quality of their glass bottles.
Interesting. Okay. So do you think it might be a requirement that there's like mandated usage of some of these outputs of the recycling by industries that can use it in order to create the demand to make it the whole system economical?
So what's happening is with Solar Sunshot program, we try to bring solar manufacturing and solar supply chain to Australia. So if one day we have solar glass manufacturing capability in Australia, that's the best route for the solar glass to go.
Okay. Megan, do you want to ask your question?
Yeah, sure. Thanks for that talk, Rong. It was awesome. I talk to local landholders a lot, and I feel they have a lot of power in having good environmental outcomes from large scale solar projects. So I'm wondering what to advise landholders for example, to insist developers do when you say, for example, to get developers to think ahead of time in decommissioning. So, what exactly should we be telling them to insist on doing?
So minimum thing is to ask the developer to put aside money for end of life decommissioning, because it's too far to say how much it will cost in 30 years time, but at least they should put some money aside, either from upfront capital, or they put some money aside from annual revenue, somehow put some money aside to deal with end of life. And that's a dedicated fund just for end of life. That's minimum.
Then, because I'm a bit confused because you said it in one point in the presentation that NG didn't go ahead with the project because it was a 10% increase in cost to recycle the panels. But then you said at another point that at scale it breaks even. So how much does it increase the cost of a big solar project, or does it break even to recycle?
So the cost of recycling today is $10 to $12 per panel. And then you add transportation, because Yas is in the middle of, not in the middle of nowhere, but very far from both Sydney and Melbourne. So recycling costs about $12 per panel. Transportation costs about $10 a panel. So that adds $22 per panel to that project if they commit that fund today. And that adds that the 10% cost for Yas project.
Okay, so it's about 10%. So, and it's a tricky thing because, there was a lot of criticisms of the CSIRO modeling of a renewable transition. And I know it didn't include decommissioning and recycling, in terms of that modeling. But, for how long do we have to manage nuclear waste as well? So it's like there's it's hard to model that one as well.
Yeah, 10% is probably on the upper case. So, but it definitely adds minimum 2%, but can be up to 10%. Really depends on the project and how far is it from major facilities.
Yeah. I've got another question. Are there many companies looking into mechanisms to turn the panels away from oncoming hailstorms? Because they're becoming more frequent.
What does that? So what to do when you have hail damaged panels?
Yeah, well, are solar companies looking at installing mass solar farms in a way so that they can turn the panels entirely upside down, and so that the rear of it can't be damaged by hail because it's got a protective layer on it or something like that? Is that being looked into at all?
That I'm not sure. I'm not sure.
Because that's something I thought. There's been lots of articles, and everyone's noticing increasing frequency of hail.
Yeah.
Yeah. There's another question. Should we have recycling plants in places that lots of solar, like central Queensland, or just have one big site recycling plant in Australia in one location? Does it make sense to be decentralized or one big one?
No. It has to be decentralized. We are such a huge country. It has to be decentralized, but not too decentralized. It really depends on the case, because most recycling technologies, if you've ever seen any recycling factory, they are huge. They are like 5-floor high and takes relatively huge land. And those facilities need many panels to be sustainable. So if for that type of facility, you probably need one in Queensland. But there are smaller, like mobile type of smaller factory that can be distributed to more regional area. But it really depends on the technology and the capability.
Yeah. Well, unless there's any other questions, I got one more. It's not really a question, but it's a suggestion. I reckon what could really help environmental organizations in regional communities is if there was a renewable energy green star rating that related to decommissioning and that company's engagement and commitment to decommissioning. I know that decommissioning is a required part of renewable energy projects now,
Mm.
currently, but whether that means exporting them overseas to be reused or recycling them in Australia, I think that would really help build trust that we could say, hey, this project and this company, they've got 5 stars in their, sustainability, full circular economy credentials. They're not just here to make a quick buck.
Yeah, there is such a thing.
Oh, is there? Cool.
Yeah, it's a race. It's called Circular PV Alliance, and I also recommend maybe I can give you the contact details. She
Yeah.
would talk from a certification perspective, and it's a great presentation.
Great. Can we get a copy of your presentation? Is that possible?
Yeah,
If you could send it, that'd be
I'll see
great.
if there's anything I need to delete, but yeah.
Excellent. Okay. Well, thank you
Thanks.
so much. And now we'll pass it over to Deepak to go down the battery rabbit hole.
Yeah.
Thank you, Rong.
So is it like you can see the full screen? Yes. Okay. So again, good evening, good afternoon, all. I am Deepak, senior lecturer at the same university, but Sydney campus from the School of Electrical Engineering and Telecommunications. I'm actually not a renewable energy researcher, but trying to contribute. I'm a telecom engineer and trying to contribute to battery safety. So it's slightly different topic, but hope you will find interesting. So the title is Improving Battery Safety with AI-enabled wireless monitoring. So we'll learn about that today. So why battery safety? So as we know that we have a lot of lithium-ion batteries around us, whether it's from the domestic usage or consumer electronics to EV vehicles or grid storage, we have them everywhere. And these lithium-ion batteries pose fire and explosion hazards. And even a small battery can have a big explosion. You may have heard news about that. Now, like Dr. Rong presented, even there is an issue of battery safety in solar recycling. And then even if there is like a battery there, a lithium-ion battery, if it uh, gets in contact with fire or explosion hazards, that is not only the reason that you can have, but you can also have some phenomena called as thermal runaway. I will explain what is thermal runaway. And this is more prominent in storage and transport. So imagine a truck containing a lot of batteries transported from one point to another, or cargo ships. You might be hearing a lot of fires on the cargo ships as well because of this, because lithium-ion batteries transport is getting more and more suffering from these explosion hazards. And what are the root causes? So root causes, there can be some kind of damage, overcharging, and there's not the cooling system not working. So there are different reasons for this failure or battery safety hazard. So to give some numbers, so there have been around more than 15,000 lithium-ion battery incidents over the last 30 years, which includes both fires and explosions. There are standards to protect these batteries, but as we know that the real world settings are often exceeding these limits. So what we need to do is we need to come up with advanced technologies that can detect such an onset way before it reaches the explosion stage, so that we can take that battery out or use the battery management system to turn around the process of overheating or whatever is causing that process to happen. So a bit of thermal runaway. Thermal runaway can happen due to different reasons. It can be mechanical. So I just to give a number. So in Australia alone, every garbage. So we have this waste management, and we always hear that you should not throw your batteries in your waste. But some people still end up throwing their used batteries, lithium-ion batteries, or their cells that they use for the electronics in their waste. And just alone in Australia, every week we have one truck fire. So garbage truck catches fire once in a week. So you can think, and why that happens, because when you throw away your battery in your waste, the garbage truck picks up the battery or picks up your waste, and it compresses the waste so that it can collect more and more waste. So that causes the crush to the battery, which can lead to fire. So that's like basically example of mechanical abuse. Then you can have electrical abuse due to overcharging or overheating. And then you have thermal abuse as well. Now, what happens is when thermal runaway starts, initial process is okay. You can actually control it before it goes to the release of heat and gas. So what this technology we're going to work on is to detect thermal runaway before it starts. So basically like an onset of thermal runaway or the signs of thermal runaway so that you can stop the process and protect the battery from getting into fire or explosion. So there are already existing methods because as we know that we have battery all around us. So it's not like there are not existing mitigation strategies. So there are cell level mitigation strategies, like each battery has their own thermal instability level, which you can raise alarm. Then you have contact based sensors, which basically are touching the battery to monitor the temperature. Then you have the module thermal management systems and the traditional temperature detection systems. So the issue with these are they are invasive methods and require the contact and have the cost and installation issues. So you can't have that for every battery, for example. So as I was saying, the current battery safety measures that we have the issue of slow response time. So they are more like reactive. They take time to detect the change and till the time already the escalation has happened and you can't prevent it at that stage. Then the issue is deployment because you have batteries all over the place. So it gets difficult to use these measures in a dynamic environment. Further, they have the limited accuracy and a lot of potential for false alarms. So you get unnecessary false alarms. And that is why you need to come up with advanced sensors which can help you to provide early warnings and timely interventions so that your system can be prevented from such accidents. So as I was saying that I am a telecommunication engineer and we are working on something called as wireless sensing. I will explain wireless sensing with more detail in the second half of the presentation. So in simple words, you can think like when you are having rainy day, your signal quality, your phone signal quality, or internet quality is not good. Why? Because the rain droplets affect the propagation of the wireless signal. So similarly, if there is anything between a transmitter and receiver, the way it behaves changes the signal quality that is received by the receiver. Now, this way, what we can do is, let's say, imagine there's a battery between a transmitter and receiver. If the battery gets suddenly hot, the receiver will be able to detect the heat signature. So that is how the technology works. So it's non-invasive because you're not touching the battery. You're far away from the battery. Is that the radio signal goes across the battery or bounces off the battery and comes to the receiver, and then you apply AI to detect. So that's the technology that we are looking at, and it not necessarily be used for detecting the surface temperature. It can be detected to use surface moisture and a lot of different kind of things. So as I was saying that the main concept is once you have detected the changes, you use the AI algorithm to detect whether that change is a normal change. So for example, between a transmitter receiver, like we know that mornings are cooler, afternoons get hot, and then evenings again cooler. So temperature change happens over the day as well. But what we are looking is temperature change or the other changes that are specific to the thermal runaway or the process of getting into thermal runaway. And we are using Wi-Fi. So all of us actually have Wi-Fi at our homes or are aware of Wi-Fi. So we use Wi-Fi signals. Why? Because Wi-Fi is readily available. The transmitter devices, receiver devices are very low cost. Another technology we are looking at is millimeter wave. Millimeter wave is a higher frequency signal. So if just to give a context, Wi-Fi that we use at our homes, you may be recognizing that we have two options, 2.4 gigahertz or 5 gigahertz. Millimeter wave is like 77 to 81 gigahertz. We are using the commercial available hardware units. They call them embedded systems or microcontrollers to transmit a signal and then receive and then apply a simple AI model to learn what is happening in between. The main advantage of this technology is it's real time. So you can detect in real time. So when the temperature is changing over time, you can track the temperature change. And the idea is that we want to use this technology for scalable real-time monitoring of batteries, especially in the transport sector. So we have a project with Trace recently started, where we are trying to develop a low-cost wireless system to monitor the lithium-ion battery surface temperatures and enhance the safety. We are using, so at UNSW, other than being a senior lecturer and academic at the School of Electrical Engineering, I'm also part of a company that I co-founded. I'm holding a CTO position there. We have developed this wireless sensing technology that can detect the temperature changes in the air. So, for example, you don't need to have a thermometer or temperature sensors to detect temperature in the room. You can actually use your Wi-Fi to detect, because when it is hot versus when it is cold versus it is normal temperature, the signal quality changes, and you can use AI to detect. So the objective is that we make a prototype that shows that it works, and then optimize its performance, conduct trials in real world environments, and develop a MVP. We are working with the researchers. I will discuss the research team plus the industry partners as part of this TRACE project to commercialize the Australian battery safety that we are proposing. So this is some screenshots from our lab recently. We had a news article on this one where we are showing how this technology works. So basically, as I was saying, we have Wi-Fi and millimeter wave radar. You can think like radio signals or electromagnetic signal going from one point to another, and whatever is in between affects them. And the role of AI is to detect those changes, which are abnormal changes. So there's a normal battery surface change, and there's an abnormal battery surface change that you want to detect. The best part of this technology is it can detect for multiple battery at the same time, because you're not touching the battery, you're away from it. And with expertise in the optimization, we are also looking at where should we place them to get to even not only tell there's a faulty battery, but even localize that battery. So there's the rack of batteries. If there's one faulty battery, you can take it out. So that is the whole idea that we have. So as I was saying, that we are working with 3 industry partners that bring the different skill sets. At UNSW, we are a team of telecommunication engineers, wireless network engineer, and energy systems engineers. So we have covered the 3 different disciplines. And then we have 3 industry partners. So the first industry partner is Guinea, that is basically the UNSW startup company that I am part of. And they have built a wireless sensing technology. The other company is Trantech. They build the hardware or the sensing hardware. So they are going to help us to design the hardware for the technology, customize the hardware for this particular application. Right now, we are using off-the-shelf devices, but the idea is to customize for this particular application. And then we have another third company, which is Deep Neural AI, so to help us to develop the AI algorithms. And with the help of our industry partners, we have already found out certain markets, especially the transport sectors, which are facing a lot of issue due to these lithium-ion batteries. So why wireless sensing? So first of all, if you can detect the thermal runaway much before it starts, you can prevent the fire. So just to give a number, when there is a fire on a cargo ship which is containing these batteries, every minute of fire is a loss of 150,000 US dollars. So every minute of fire is 150,000 US dollars, and current fire sensing technology takes 30 minutes to detect. And we know that we are in the middle of nowhere when we are on a cargo ship, so it's a lot of damage. Second, the cost is very low. So the Wi-Fi chipsets are 100 times cheaper than the current fire detection cameras, thermal cameras that are used in the systems. Then the environment, because you can actually provide the safe lithium-ion battery use that will help you in using renewable energy, aiding the decarbonization and clean energy goals as part of the TRACE project. All right, so next steps. So I will discuss some lab results. So we have done actually some lab results already, and now we are in the stage of doing it in the real world and collect the data. Once we have the data, we optimize our AI algorithm. And once we have done that, we kind of improve our AI model and the intentional sensor for better accuracy and reliability. We are already having strategic partnerships with the logistics sector company. So there's a very big logistic company, transport company in Sydney that we are working with, and also looking to work with the energy sectors through our energy systems colleagues. So the aim currently, the technology is around TRL level 6. So TRL is technology readiness level, which is basically we have tested it in the relevant environment. The aim is that over the next 1.5, 2 years, we reach to the TRL level 8 plus. So 8 plus would be like pre-sales. So make the product, and before you sell it, or it's like the MVP kind of version of the product that we want to develop over the next 1.5, 2 years. So as I mentioned that the team that we have the academics from UNSW Sydney and the industry partners based in Sydney again. So now I'm going to discuss what is Wi-Fi sensing or wireless sensing in general. So if you see these two screenshots, so these screenshots are from the movies. I don't know how many of you recollect. The first one is from Mission Impossible, while the second one is from Batman. And as we know that these are science fiction. So what are science fiction? Basically something that is a fiction, which is not reality. But with the help of this technology that I'm talking about, Wi-Fi sensing or wireless sensing, actually this has turned into reality. So what is the first image showing? First image is showing that there is a person who is trying to enter a authorized or like a restricted area. And there is a technology which kind of profiles the person. It's like you can think like something like an X-ray kind of thing and tells whether the person is the person who is allowed to go or not. Imagine with the help of Wi-Fi, each one of has a Wi-Fi ID. So the way we affect the Wi-Fi signal is unique. So I have a unique Wi-Fi ID, and you guys have different unique Wi-Fi ID. So you can actually use your Wi-Fi profiles to detect a person. Similarly, in the second photo, the Batman photo, what is happening is that this guy is monitoring the entire city through the cameras that are there in the city. Because the Wi-Fi signals is all around us, and we can track people, identify people. We don't need these cameras. We can use the Wi-Fi signals to have the vision of the city to monitor how many people are there, who are there, and where are there. So the applications are a lot, like from counting people to tracking people, monitoring gestures. Imagine you are going to an ATM machine, typing your passcode. You can detect from the finger movements without picking. So that is the power of this technology. And in terms of environment, it can detect humidity, wind, thermal, fire, gases. I will show some results. So why this one technology is able to do everything? Because anything that affects the radio signal going from one point to another leaves a signature that can be recognized using the AI algorithms. You can detect that particular activity. And the advantage is it's much low cost, plus there's no maintenance. For example, if you compare with a camera-based technology, you need to clean the lens, maintain the visibility of the camera. Here, as you know, Wi-Fi signal can work in the night. Wi-Fi signal can work even if there's a person in between, there's a wall in between. Like in our homes, when we have Wi-Fi in one room, we easily get the Wi-Fi in the other rooms. And why particularly Wi-Fi? This could have been any wireless signal, because 53% of the traffic that we have around us is based on Wi-Fi. And Wi-Fi actually is coming with a new standard which will be used for sensing applications. So those of you who are aware of this 4G, 5G, 6G concept, as we are going towards sixth generation of mobile networks, our mobile phones will not be able to communicate, but will also be sense the environment. So that's why Wi-Fi sensing has a lot of potential in this domain. So as I was saying, that how it works is that we have a radio signal that goes from the transmitter to receiver, and then things between affect it. Once you receive the signal, you apply some filtering to take out the noise, and then apply the signature matching or pattern matching to detect what happened. Okay, so those of you who are aware of Wi-Fi, you may be knowing that Wi-Fi is based on a technology called orthogonal division multiplexing, which means that the same Wi-Fi spectrum can be used by multiple users at the same time. So why I'm sharing this is because the Wi-Fi signal that we get at the receiver is a huge amount of data. It's not like one data sample. At every instance, we get multiple data points because it uses different frequencies. And every second you actually can transmit a lot of. So every second you get a lot of data. So it's a lot of data that you have at your disposal to make the decision. So currently, as I was saying, that we have not customized the hardware. We are using the off-the-shelf hardware, which is called Raspberry Pi or microcontroller. Basically, it is transmitting a signal from the transmitter to the AP. And then there's a guy or there's another Pi who is listening. And the job of this Pi is just to listen to the communication or the Wi-Fi signal. And based on the signal that it receives, it can find out what's happening in between. So the main technology that we have is basically based on so you can reproduce these results. So all the results that we have, they are reproducible. So basically, once you receive the signal, you apply a third-party tool to get the signature, and then you apply filtering techniques to filter out the outliers and the noise, and then apply the machine learning to detect the phenomena. So why we should use Wi-Fi sensing for fire detection or hazard detection? Why not what's the advantage that we have? First of all, the power consumption is really low. These Raspberry Pis consume a very low amount of power as compared to other technologies. So even with a small battery, they can last for months. So you don't need to change the battery frequently, and they can actually run on solar panel power, small solar panels as well. So very little power they need. Second, installation is very easy. The location doesn't matter, that they are robust to that. They are dynamic environments. You can easily install. It's like a plug and play. You take your device, just put it there. You don't need to worry about the visibility and all that. And we will have already shown that the accuracy is very high. Plus, the maintenance is very easy. Like you don't have to do cleaning and all that. So all these advantages makes Wi-Fi sensing a good solution for fire detection. So as I was telling the example of the garbage truck fire. So you can see that this is the fire happening from on a garbage truck, and then this is the fire happening at the battery plant, and this is the fire on the cargo ship. So you can see that the thermal runaway causing this battery hazard is across the different sectors. So what we are trying to do is we're trying to get the early signs. So if we can have the signs of the abnormal rise of temperature leading to thermal runaway, we can actually take some action, a timely action to protect from entering that thermal runaway stage. So we know that there are a lot of conventional ways to sense temperature. You have surface temperature, there are RFID-based temperature sensors, there is a thermal camera that you do, but all these have the issue that they need line of sight or they are contact based. Plus, they come at additional cost. So you need to have a dedicated sensor for these kind of applications. So how the Wi-Fi sensing works? So if you have a transmitter and receiver and there's a target object in between, or there is a hot surface in between, then what happens is that when I can give a simple example of like those of you who play any ball game like cricket or tennis, you know that the surface plays a role in how much the ball gonna bounce. So for example, we know that in Western Australia, in Perth, we used to have high bounce because the pitch was like that. Similarly, let's say with the cement floor, the ball will bounce more. If it's a grass floor, it will bounce less. Why that happens? Because the refractive index or the material of the surface decides how much of the energy will be absorbed and how much of the energy will be reflected. Similarly, when something gets hot or something is cold, the amount of energy that gets absorbed and reflected of it is different. And that is why the reflected signal of a hot surface versus cold surface has a different signature, which can be detected using a AI algorithm. So that's what I was explaining, the theory behind that. So the refractive index of the surface, hot versus cold, is different. And this difference in refractive index can be utilized to detect the surface hotness. So we did this experiment in the lab where we had this silicon heater belt that you can see in the middle. It's there in the middle. And sorry, it's in the middle here. You can see the silicon belt in the middle, and there's a transmitter receiver. And when the signal goes through it, you can detect the surface temperature. So the surface temperature, you can see the accuracy is very high, 25, 31, 33, 35. So you can even detect 2 degrees Celsius change with a very high accuracy of 96%. Another thing that happens in the thermal runaway early warning is gas release. So there is a gas release that happens. So you have a gas release. So this technology can also be used to detect the gas. So in this experiment, we have shown that we can use this technology to detect different gases. So for example, carbon monoxide gas. So when you have different amounts of carbon monoxide gas, we are able to detect with very high accuracy again. This experiment was done in a chemical engineering department that we have, because CO is a harmful gas, so we cannot do it in the open air. So we tested for different levels of CO. So first we had no gas, then we have only nitrogen gas, and then we started to add different amounts of CO, 80 parts per million, 150, 200, 400. And we can see again the accuracy is more than 98%, which means that not only the amount of gas, but the kind of gas also leaves a different signature. Then the another thing which we had tested was to detect temperature. Can you detect the temperature? So in this experiment, for example, there is a heater between the transmitter and receiver, and what you can see from here is as the temperature goes of the heater from 25 to 35 degrees Celsius, the CSI is, or the radio signal strength, is decreasing. So you can see there's a correlation between the radio signal strength and the temperature increase, which can be exploited to detect the temperature changes. In this experiment, we showed that if you even turn a small stove, you can detect the flames as well. So, but flame is way too late because that has already caught fire. We want to detect, but you can detect even flame, the small heat change that the flame can bring in this flame of a stove. As you can see here, before, during, and after are three different events which we can distinguish. Not only in the lab, we actually did this test in the Sydney Harbour Tunnel. So those of you who have been to Sydney, there's North Sydney, South Sydney, and we have this underwater tunnel. And right now they have the world-class sensing technology to detect fire, but they have a lot of false alarms. So every 2 years they do a test where they actually put a car on fire. So as you can see in the screenshot, there's a car so we were there at the right time, right place. So we put our sensing devices there, and when they actually turn when they put the car on fire, our technology was able to detect way before it actually gets into the explosion, like within 1 second, and the accuracy was plus minus 0.4 degrees Celsius. So we were able to report that, and this actually made a lot of news. Actually, we did not start our company because we wanted to start it. We started it because we were invited to start or open a startup company due to this experiment. Because this experiment was covered by UNSW newsroom, which was then picked up by the third party the electronic media, which reached to UK. And the Lloyd's Registry of London, who is a shipping insurance company, they reached out to us to do a pilot with them to detect fire on cargo ships. And that's where this company, Guinea Guy, was started. So as I was saying that when we were shortlisted to run a trial with the cargo ships, their challenge was you have the containers inside the ship, and one container may have something inside it which will lead to fire. Now, current technology, how it works, it sucks in the air from the hold and puts it over a sensor or gas sensor or temperature sensor to detect if there is, or a smoke sensor in a way to detect where there's a fire. So it's not a proactive, it's a reactive. So smoke has to come out to detect. Whereas what happens in our technology, as you can see in the GIF, so for example, the third one has this has a heat source inside it. So over time, what will happen is before the smoke and everything, as it's a metallic structure, when there's something inside burning, it starts to heat up the surface. So you don't need to have the smoke coming out. Even if the surface temperature changes over time, our radio signals, which are going at the speed of light, can strike off this and come back. So you can not only detect early, but you can also detect the location. So currently, there is no technology we can tell you the location of the heat source, but with this one, you can even tell you the location of the heat source. So that's the test we did in the lab to show that it works. And then we actually did it on the lab. And as I was saying, that installation is very easy because on the cargo hold, all these are metallic walls. You can just stick the sensor that we have. So this is like a sensor box which has a battery in it and the transmit receiver. And in this diagram, what we are showing is you can also, so this is the real world data that we had did experiment on the Evergreen ship, Evergreen's Balmy ship. And this ship goes from Sydney to Asia. And what we were showing in this is that even if there are some reefer containers whose temperature goes up and down, you can detect almost with full accuracy the temperatures changes inside the ship, even when the ship is moving with all the, like waves and thunderstorms, you can detect with good accuracy. And this was the actual fire and smoke detection experiment. As you can see that we went to a yard and we actually burned a few things to see how quickly we can detect. And this was one test that we did to show that you can detect it much like you can detect even smoke before the fire. So there are different kind of tests we have shown that it works. So finally, I would like to thank the team and the Trailblazer grant and the three industry partners, Trendtech, Deep Neural AI, and Guinea Guy. This is a photo of the recent news article that I mentioned. We have our team members. We are missing a few academics and our Trendtech team, but this is more or less the team that we have. And I will stop with the video that explains the technology. So these are the current fire sensing technologies. As you can see, the smoke has to reach them. These are found in our homes as well. And this is when we were shortlisted by the Lloyd's program. And they shortlisted us as the disrupting technology. And we have been working with them since then, over a year now. And these are shipping partners that are part of the program. It all started with the Sydney Harbour Tunnel, but now we are working with the logistics company to detect different things. So yes, you can detect even aerosols. Uh, you will be surprised you can detect wetness of a diaper. So if the kid has or the child has uh, wet the nappies, you can detect that as well with this. So this was the fire experiment I was talking about. And this is the logistic yard where they want to detect human versus machine. So, and these are the advantages which I mentioned about the technology. So we are already in the process of getting our product certified and running the pre-sales trials with the industry partners. So that's pretty much. Thank you. Any questions?
Thank you so much, Deepak. Awesome work. Really appreciate it.
Thank you.
I've got some questions to help.
Yes.
Does other people have questions as well? Put your hand up if you do. I might start us off. Just with I can see how, yeah, like heat detection is really useful whenever a battery is in use or before sale. I'm curious about, is there any technology solution that can be like put on garbage trucks so that batteries kind of like send out a signal that they can detect whether it's in a curbside bin and go, okay, we're not taking that one. We're not going to put that into the truck. Like like a permanent little sonar or something like that the garbage truck can easily have technology to detect.
Yes, yes. I don't know whether I can share that because that's we have an NDA with a garbage truck company called Veolia, if you have heard, and J.R. Richards. So yes, but that is slightly different. Here, what we, like you said, we're detecting the heat changes that happens. But in the garbage truck, what happens? There's just a battery lying down there doing nothing. So yes, the short answer is yes, we can detect, but we are not doing that as part of this project. But yes, if there is a battery in the bin, you can detect.
Yeah.
We're still working on it because it depends on what kind of waste is there as well. So
Yeah.
if there's kind of like a paper kind of waste, it's easy to detect. But if you have tin and metallics and all that, it becomes a bit challenging.
Harder to
We
detect.
Yeah, we have tested it for cardboard kind of waste. We are developing the algorithm to do it for any waste.
Yeah.
And the idea, like you said, is we can detect in the bin itself. So before the truck comes and picks it up, if you can detect in the bin, then the truck driver will not pick up that bin.
Yeah.
And there will be some kind of check and to prevent those kind of fires. Yeah.
Yeah, because your technology solves the problem
Yeah.
when the battery's in use or before sale. But if
Yes.
it's been thrown in the bin, and into the garbage truck, well, then it's like if it's no point because no one's monitoring to see if that alarm goes off in the heat.
Exactly,
It's in a
exactly.
garbage truck. But
Yeah.
that would require international kind of standards that every battery has those little sonar kind of detection systems, or is there a way that it could be detected in just the way that the battery is currently manufactured?
So it depends on different things like size of battery, type of battery. There are different kind of things. So currently we're focusing on the lithium-ion batteries. Uh, but yeah, so it's not sonar, but but I understand what you're trying to come at. It's like kind of a radar sonar kind of that area, but we are using the Wi-Fi signals at this stage.
Yeah.
We haven't tested for all the batteries, but the few batteries that we have tested with the cardboard waste, you can detect with accuracy of around 80 to 85%. Doesn't matter how much of waste is there in the in the bin, but only cardboard kind of waste, like paper waste. But it's very difficult to generalize. So we went to a waste yard to actually go to the test on the real bins, the smelly ones as well. And, yeah, so we collected data. We see that the current version of the algorithm is not that accurate because if you've not seen the waste, different kind of waste also has a different signature. So we are working towards generalizing it. But as I mentioned, that's not part of this project.
Yeah.
But yeah, like you can see this file. So this is the
Yep.
application we are discussing. Yeah.
Very
So
good.
currently what happens is, sorry, just to complete. So currently what happens when there's a fire, they have to dump it,
Yeah,
somewhere.
that's
Yeah.
it.
Yeah.
Well, that's really good. It's awesome to know that that is all happening. I just wish people were a bit smarter and didn't chuck them in bins.
Yeah. So they actually asked us we asked them where is the best place, and actually we think the bin is the best because what they were saying, another option is when they take the bin and turn it around, and the contents are out in the open. Because the advantage with that is you don't need to put the sensor on the bin. You can just put the sensor on the truck. Because otherwise you have to put like a sensor on the bin as well, like a transmitter on the bin as well. So we're still looking at the cost aspects and other things, because then we have to work with some council for the bin, like if you have to
Yeah.
put on the bin. Yeah.
Jane's got a question. What happens after a temperature rise is detected? How much
Yes.
time do you get to, before it catches fire?
Yes. So, like we can detect like even a less than 1 degree Celsius change within a second. So we can detect it much faster. And there is a time for it to actually run into that thermal runaway state. So it doesn't happen like instantly. So the idea is we actually integrate so we are a detection technology. We are not, we don't stop it from happening. We just detect it. We just raise the alarm. So the idea is we integrate it with the battery management systems. Once we raise the alarm, the battery management system will be able to either, let's say it's happening due to electrical abuse, it will take out the battery from the circuit so that the battery doesn't stop to overheat. So those kind of connections we need to, or like the fire mitigation strategies we have to integrate our technology with, because we are alarm raising company, or like our technology. Yeah. So for example, for the fire on the cargo ship, we have 30 minutes to beat. So current technology is 30 minutes. So even if you take 5 minutes, you still save 25 minutes. So it's based on a different application. In case of the garbage one, it's before the truck compresses it. So
Yeah,
it's
right.
it's at different times. Yeah.
Awesome. Is there any other questions from anyone else? Been such a good, informative presentation.
Thank you. Thank you. If there's any question, feel free to. I'm happy to share the slides, and
Yeah,
if there are any follow-up question, yeah.
if you could send
Thank
the
you.
slides, that'd be great. Well, thank you so much, Deepak, and thank you, Rong, if you're still there. We'll finish the recording now, and yeah, really appreciate you sharing this information. And it'll go on our website. We're building a renewables kind of information website to address a lot of questions and disinformation about renewable energy and battery storage technologies and different things. Yeah, it's complicated, so it's hard. We've got to have conversations in an educated public because it's not an easy transition, and we've got to make sure it's got integrity. So thank you both for your important work in helping to yeah, make a clean energy transition possible, and yeah, to act on climate change. We really appreciate it, yeah, at that technical level.
Thank you. Thank you for having us.
Okay. Thank you so much. Okay, see you
you.
later, everyone.
Bye. Thank you all. Have a good evening.